So in this video, we're going to be looking at the conservation of energy. And your learning intentions for this video are that you need to be able to describe energy transfers between objects within different systems. You need to know that energy is conserved when transferred from one object to another in an isolated system. And an isolated system is a system that is free of external forces such as frictional forces and air resistance or drag forces. You need to be able to also solve problems using the conservation of energy, and this will definitely be in your test. So as we've discussed before, there's a relationship between work and energy. When you do work onto an object, that object gains energy. So for argument's sake, if you apply a force to a shopping trolley and you displace it, you're doing work, because work is force times displacement. And that shopping trolley is gaining kinetic energy. So the amount of work is equivalent to the gain in kinetic energy. Okay? So energy acquired by objects upon which work is done can be either kinetic energy or potential energy. So for argument's sake, if you're lifting up this barbell, so you're doing work, you're applying a force, you're displacing the barbell, and you're actually giving it stored energy or gravitational potential energy. Now, that is why we often describe or define energy as the ability to do work. It enables you to apply a force to an object in order to cause a displacement. So energy is the ability to do work. Now, the law of conservation of energy is just that when basically energy is conserved when energy is transferred from one object to another, but in an isolated system. So it has to be free of external forces such as friction and air resistance. So basically, if you're asked to define the law of conservation of energy, so the law of conservation of energy states that energy cannot be created or destroyed. It can only be transferred or transformed from one form into another. So we've looked at it in the skate park interactive, where gravitational potential energy was transforming into kinetic energy when we removed friction. And then, so at the top it was all GPE. And then there was, if the skater ramp, it was all GPE at the top, and then at the bottom it was all kinetic, and then on the way back up it was all GPE, and GPE transformed into kinetic. So halfway down it was half GPE, half kinetic, etc. So here's a little roller coaster. So at the top, lots of potential energy, low kinetic. On the way down, it's at its maximum kinetic energy because at the bottom, little and no or low potential energy. And then as it gains a bit of height, gains a bit of potential energy and loses a little bit of kinetic energy. Okay, and you've seen that in the skate park interactive. So again, at the top, this is just a skier, another example. At the top, they have 0 joules of kinetic energy, 50,000 joules of potential energy, and then on the way down, it's changing. They're gaining kinetic energy, losing potential energy. Gaining kinetic energy, losing potential energy. And as they go high again, they gain some more potential energy, lose some kinetic energy, and then right at the bottom, all their energy is kinetic energy. Obviously, in reality, we have friction, so obviously the skier is losing energy on the way down due to friction and air resistance, but in an isolated system, energy is conserved. So we're going to do a couple calculation examples. So first one, a ball is dropped from rest. So it's got an initial speed of 0 at 3 meters above the Earth's surface. Calculate the speed with which the ball will hit the ground. So all that's happening is we have a ball and it's being dropped. So at the top, so at position 1, okay, we all only have kinetic energy. At position 2, we only have potential energy because it's stationary. At the bottom, we're going to have all kinetic energy. So we know that energy is conserved, assuming no energy losses occur in its free fall. So basically, we can say that all the energy at position 1 is going to be equal to all the energy at position 2. So we can set that all the potential energy at position 1 is going to be equal to all the energy at position 2. So how do we calculate potential energy, gravitational potential energy? It's just mgh. And that's going to be equal to the kinetic energy at the bottom, which is going to be half mv squared. Now, in this question, we're only given the initial speed, so we know it's got no kinetic. It's 3 meters above the Earth's surface. So the only thing we're actually given is we're given the height is 3 meters. We're not given anything else. So all we've given is height. We know gravity, 9.8. But can you look at this equation? You can see that there is a mass on both sides of the equation. Well, we can simply cancel them out. And then we want to rearrange this equation for speed, because we want to find speed. So to get rid of the half, we need to times both sides by 2. So we'll get 2 lots of GH equals V squared. And then to get rid of the square symbol, we need to do the opposite of squaring something, which is square rooting. So we're actually going to get the speed is equal to the square root of 2 lots of times the acceleration due to gravity times by the height. So we can type that into our calculator, and the speed is going to be 2 lots of 9.8 times 3. And we'll get 2 times 9.8 times 3 square root is 7.67 to 2 decimal places. And that's meters per second. So it's traveling, so all we needed was how far above the Earth's surface, and theoretically if there's any energy losses, it should have been traveling at that 7.67 meters per second. Now we're going to do one more example. The second example is we have an arrow. This time it's fired with a vertical velocity. So an arrow is fired, so we're down on the ground, we're firing an arrow upwards with a vertical velocity of 20 meters per second. Use the law of conservation of energy to determine the height reached by the arrow. So basically what's happening is the arrow is being shot up. At some point when it reaches its max height, what's the speed of the arrow going to be? It's going to be stationary. So its final speed is going to be 0 meters per second. Alright, so starting off down on the ground, finishing up in the sky. So at the ground, it's not written in the question, and it's something that we could assume at the bottom. So something that we've assumed. So we're going to assume that the arrow is shot from the ground. So realistically, when you're shooting an arrow, it's going to have a little bit of potential energy because you're a little bit above the Earth's surface when you're firing the arrow. But we're going to assume we're shooting the arrow from the ground. So at the bottom, it's going to have all kinetic energy. It's not going to have any potential energy. And then at the top, when it reaches its max height, it's going to have no kinetic energy because it's stationary, and it's going to have all potential energy. So we can set these two equal to one another. So the kinetic energy at position 1 is equal to all the potential energy when the arrow is up in the sky. So we know the formula for kinetic energy. It's a half mv squared. And we know the formula for gravitational potential energy is just mgh. And again, the masses cancel out. So mass doesn't really have an effect if you're assuming that there's no external forces. And then for this one, we want to actually, what are we trying to solve for? Use the law of conservation of energy to determine the height. So we want height. So all we need to get rid of is g. So all we're going to do to both sides of the equation is divide by g. So we're going to have that the height is equal to a half v squared divided by g. So if we type that into our calculator, we'll have a half times by v squared, which is, it got shot up with a initial speed of 20. So 20 squared divided by the acceleration due to gravity, which is 9.8. Then if we type that into our calculator, half times 20 squared divided by 9.8, we'll get that it's going to reach a height of 20.41 meters. And then I'm running out of room, but some assumptions we've made. Well, one, the arrow was shot from the ground. And the other major assumption we've made is that there were no external forces. So no external forces acting. In brackets, air resistance. So, have a go at the questions. Questions 15, 17, and 79. Cheers.